Now we have a logistic regression model and a log loss function. And we know that applying this log loss function is equivalent to maximizing the likelihood of the data. The loss function looks a little alarming, and so it's a good idea to examine exactly what it is in the context of an example and see if it does something sensible. So here's a question. We have a data set of exactly 2 points, minus 1, 1, and 1, 0. And we are going to fit our logistic regression model with our log loss, which is provided here for reference. To simplify matters, we only have one covariate, one x, so you can imagine it on just the horizontal axis. And there's no transformation. Phi of x is just x. So the question is then, what is the best theta in this case? Now, theta, it should just be a scalar. We only have one feature, and so this is just going to be some number, we think. So what number is it going to be? And there are 4 choices here. Let's see if we can eliminate some of them. The logistic function that we have drawn looks like this, but clearly the probability is 1 for negative x and 0 for positive x, so we should end up with the function flipped over. That is signaling that theta should be negative. But exactly how negative? Is it minus 1? Is it minus infinity? Is it actually none of the above? Well, let's see. The plan is that for each of these points, we will work out exactly what this contribution is. And then we will plot those contributions. We'll plot the average of the contributions and see which theta gives us the minimum value. So we're now going to consider the point minus 1 to 1. And just crank out these pieces one by one. So when we just look at one point, you don't have to think of any of this, though you know that n is equal to 2. We're just going to look at what's inside one single term. And so y for this point is 1, x is minus 1, and we took phi of x equals x. So for this point, phi of xi is minus 1, y is 1, so all of this is minus 1. It's just a number, it is its own transpose, and that's why you have minus 1. X is minus 1, so phi of x is minus 1, minus of that is 1. Take the transpose, it's still 1. And so here you have minus 1 times theta, and here you have log of sigma of theta. But don't forget that there's a minus here. So the minus 1 times theta times this minus gives you a positive theta, and then the plus log of sigma theta with a minus sign in front gives you minus log sigma theta. That's just a function of theta. We can plot it. And it looks like that. Now for which theta is it at its minimum? It looks like the theta for the minimum is just drifting all the way out there. And what we're learning from this picture is that the best theta is actually as far out negative as you can go. And that's a bit of a problem because we would like the best theta to actually be a number, but it is just trailing off to minus infinity. For the next point, I'm going to ask that you do the details exactly as we did here, And you will see that for the point 1, 0, once again, the best theta goes off to minus infinity. You can calculate y times phi of x transpose. You can calculate minus phi of x, plug in, and your objective function is 0 minus log of sigma of minus theta. And you plot that, and once again, theta is just rushing off to minus infinity. So we already had theta going to minus infinity for our first point, and now we have exactly the same behavior for the second point. So no big surprise when you look at the total loss, or average the loss across both of the points. Your best theta is still rushing off to minus infinity. And what does that mean in terms of our actual prediction for whether we're going to get a 1 or a 0? For that, let's remind ourselves of what the model is. The model is that the probability that your response is 1, given the covariates, is sigma of, well, we used to write phi of x transpose times theta. Now phi of x is just x by assumption here. And there's only one x, so this is just x times theta. It's very easy. So as we know, the best theta is heading off towards minus infinity. And so let us see what happens to this prediction as theta goes to minus infinity. If x is positive and theta is going to minus infinity, then x theta is also going to minus infinity. Remember your logistic function. The logistic function that we drew is 0 at minus infinity. And so what we are doing is we are predicting that if x is positive and your best theta is herring off to minus infinity, then your prediction is 0. That is the chance that your label is 1 is 0 out here. And similarly, if x is negative and theta is going to minus infinity, then x theta is going to plus infinity. And the logistic function there is 1. And so we are predicting that on the negative side, the probability that the label is 1 is actually 100%. We're predicting 1. And we have a very degenerate solution. It just says on one side of the vertical axis, you are certain to get 1, and on the other side, you are certain to get 0. This is a little overly optimistic because in your test data, you might have a less clear picture than you do now. The picture that we have says that there is one point here, and which is a 1, and another point here, which is a 0. So we can just slice the plane down. We can put a separation between these two regions. And this kind of separation causes a problem when you are fitting a logistic regression model. So linearly separable data look like this. In this picture, we are imagining we have two covariates, so one on this axis and one on the other. And you can think of these as the ones and these as the zeros. On the plane, the ones are in this upper triangle and the zeros are in the lower triangle. We can clearly put a line that separates them. A hyperplane is just a plane which has a dimension lower than your space. So in the case of two-dimensional plane, it's a line. So basically you can separate these two groups perfectly. Usually the world isn't like that. Usually there is some degree of uncertainty. So here, most of the zeros are down here and most of the ones are up here, but there is a zero also up there and there is a one also down here. This is much more typical of data in the world. And so you have to give yourself a little bit of uncertainty in this boundary region because you can have these kinds of crossovers. So any prediction that says on one side of a line it's 1 and on the other side it's 0 definitely needs to be made a little more sensible. And it turns out that for logistic regression on linearly separable data, you have to regularize. Otherwise, your weights go off to infinity. We had an example in where the theta was going off to minus infinity. So the solution is to use regularization. You have the original loss function, and then you have this lambda times some penalty that you give yourself, and just squaring the thetas is often good enough. If the points are such that these thetas start heading off to infinity or to plus infinity, then theta squared is going to be very big. And so any small positive number here times this sum is going to cause your loss to get very large. And so this helps, like all regularization, this helps to keep your loss under check. And it prevents your weights from going off to infinity. So here is the picture that we had drawn before. Here is the loss without regularization. And here is the loss with regularization with lambda chosen to be 0.1. It's really your choice, which you should do by cross-validation. But in this case, we chose 0.1. Notice that it's the loss plus 0.1 times theta squared. There is only one theta. So this sum only has one term. And you can see how this now has a clear minimum, which is about -1.